type of polynomial functions we're going to look at are called power functions. Power functions have a format: f of x equals k times x to the p. Two special cases are when p equals 0 and p equals 1. If p is 0, the function simplifies into f of x equals k. X to the 0 is 1, k times 1 is just k. That graph is a horizontal line with a y-intercept at k. If p equals 1, the function simplifies into k times x to the first. That graph is the direct variation plot, where the slope is k and the y-intercept is the origin. The two general cases we'll look at are when p is odd. In other words, f of x equals k x to the 3 or 5 or 7 or 9. And if p is even, we wind up with a family of functions k equals x squared, or to the 4th power, or to the 6th power, or to the 8th power. In general, these families of functions have the same shape. The odd functions are going to look like the snake functions that travel through the origin, and the even functions are going to look like the parabola functions that also travel through the origin. So let's take a look at these functions, these last two, in a little bit more detail. So to explore the family of power functions when the exponent is odd, we're going to start with the familiar x cubed function. You can see that this is the x cubed function by looking at the name down here. It goes through 0, 0, 1, 1, and negative 1, negative 1. If I compare that to x to the 5th, which is the next highest odd function, and then also include x to the 7th, we can see some commonalities between the three types of functions. They all travel through the points 1, 1, 0, 0, negative 1, negative 1. They all have the snake-like shape. The difference is that as the exponent gets larger, like the red x to the 7th function, it appears that the shape grows up and down faster. The exception is when you're between negative 1 and positive 1. X to the 7th hugs the x-axis a little bit longer as it travels away from 0, until it goes through 1, 1, and then starts to increase much more rapidly than x to the 5th or x to the 7th. So all the odd functions will have this S-shaped graph that go through 1, 1, 0, 0, and negative 1, negative 1. If I turn those off, we can explore the even functions. Here's the familiar parabola. We notice that it goes through 1, 1, negative 1, positive 1, and 0, 0. And if I draw an x to the 4th and x to the 6th, we can see that all the even functions are also U-shaped. As the exponent gets larger, x to the 6th travels up much faster than x to the 4th or x to the 2nd. So as the exponent gets larger, the shape of the graph gets narrower. Again, the exception is between negative 1 and positive 1. X to the 6th hugs the x-axis a little bit longer than x to the 4th and x squared, and once it reaches 1, 1, that's when it starts to increase much more rapidly than the other two. So the summary is that odd-shaped functions have an S shape, and even-shaped power functions have a U shape. Here are two examples of graphing power functions that involve transformation. In the first, we have an odd exponent, which means the original shape will be the S-shaped graph. The negative here indicates a flip across the x-axis. The 3 is a scale factor. And the plus 2 inside the parentheses means a shift left 2 units. In order, a flip across the x goes first, left to right goes second, and scale factor is the third thing. So if the original S-shaped function starts at 0, 0 and travels through 1, 1 and negative 1, negative 1, a flip across the x-axis would move the point up here down to positive 1, negative 1. And the original point that was at negative 1, negative 1 gets flipped across the x-axis up here. To pick up this entire group and move them left 2 units means my new starting point is at negative 2, 0. And to incorporate the scale factor of 3, when I go left 1, I'm going to go up 3 units, and down 1 right 1, down 3 units. So connecting the big dots produces a rough sketch of the fifth degree power function, including its transformations. The second example has an even exponent, which means the original shape is a U, kind of like the parabola. Again, we've got to flip across the x-axis. X minus 3 indicates a movement of right 3 units, and then when the entire thing is divided by 2, my scale factor this time around is 1/2. In order, flips across the x go first, left and right go second, and I'll worry about the scale third. If I take a parabola that starts at 0, 0, and normally goes right 1 up 1 and left 1 up 1, and flip it across the x-axis, I've now got 2 points down here, or my parabola opens downward. The fourth degree power function is going to be moved right 3 units, so that my new starting point is here, and a scale factor of 1/2 means that I will go over 1, down 1/2, over 1, and down 1/2. Since I can fit more points on this grid, I'm going to start here, move over 2, raise that to the fourth power, which is 16, but then cut that in half and get 8, which is a little bit off my grid here. Same thing for this one. If I go over 2, 2 to the fourth is 16. My scale factor is 1/2, so I can go down 8 units, which again is a little bit off. And 2 other approximate points on either side, where I can draw a rough sketch of that power function. So that's it.